Hi, my name is Ansh Gupta. I'm from Team 26929 Pioneer 1 and 4213 Metal Cow Robotics. In today's video of part 2 of learning odometry, I'll teach you how to code the field-centric drive control. Additionally, if you haven't seen part 1, I'd recommend you to go watch that first to get a better understanding of this entire 3-part series. In today's video, you might see how it's 20 minutes long, and the reason for that is I have shown you step by step how to get to my code, starting off with what is field-centric drive control, then talking about how to get inputs from your code, then talking about deriving equations, how to get equations for all 4 motors, and then finally the coding piece. In the coding piece, I've gone line by line showing you every single section of how to code this field-centric drive control. I really hope you watch this entire video to get the full understanding of how the code works and the math behind every single concept. But if you don't want to do that and you want to skip around a little bit, I've added timestamps right here where you can navigate through certain sections of this video to get a quick understanding of certain topics. Overall, thanks so much for watching this video, and let's get started. Before diving into field-centric drive control, we'll first look at the most common example of teleop that teams like to use, which is robot-centric drive. Here I have an example of what robot-centric drive is. On the left, I have a gamepad, and on the right, I have a robot. The vertical line in the middle tells us what is forward relative to that robot. Then we have red marks that help us find the position and movement of the joystick in the robot. So for starters, if the robot is facing forward and the joystick is pushed forward, the robot will continue to move in a forward pattern. However, if the robot's now facing to the right and the joystick is still pushed forward, the robot will move towards the right. Again, if the robot's at a 45 degrees angle and we continue to push forward, it'll just move along that diagonal line. So, in simple words, robot-centric drive is where the robot will move relative to the robot's axis and where the robot is facing. Now, here's where field-centric drive can come into play. For example, if you continue to push forward while the robot's facing forward, it'll do the same thing as robot-centric drive, which is going forward. However, if the robot's at a 90 degrees angle and you still push forward, no longer will the robot go to the right, but rather it'll go to the left relative to itself. So in this case, the arrows on the joystick and the arrows on the robot will now match. Similarly, when the robot's at a 45 degrees angle, you can still see how when you push forward, the robot will go forward relative to that same arrow given from us from the joystick. So the big idea here is that the arrows now from the joystick and the robot will match. So in words, the field-centric drive is where the robot's movements are directly tied with the field's orientation rather than the robot's own orientation. Now let's take a look at how we can get inputs from the gamepad in order to control our robot. On the left, I have the gamepad with a coordinate plane on the joystick. If you push forward, you want the robot to move forward, and that will be Y positive. If you push your joystick to the right, you want your robot to strafe to the right, and that will be our X positive. On the right side of this slide, I have the X power, the Y power, and the joystick. Currently, this joystick is in the middle. That means X power is equal to 0 and Y power equals to 0 as well. This means this is our origin. Now, if you push forward on the joystick, you now have a positive 1 Y power and you continue to have a 0 X power since you haven't pushed to the left or right. Similarly, if you push to the left, you now have a negative 1 X power and you continue to have a 0 Y power since you haven't moved up or down. Lastly, if you push the joystick to the top right, you now get 0.75 for your X and 0.75 for your Y. Now that we have two values, let's take a look of how we can use these inputs
in order to supply the correct amount of power to each of our mecanum wheels. Here we have the equations for the front left motor, front right motor, back left, and back right.
First, it's important to understand the robot's coordinate system. Going forward is positive x, strafing to the right is positive y, and going in a clockwise direction is positive t. So starting off with our first image in our equations. If we go forward in the x positive direction, all four wheels have to be positive. So that's why we add positive x to all of our equations. Then looking at strafing to the right, which is positive y. As you can see, front left is positive, front right is negative, back left is negative, and back right is positive. So we apply those positive and negative y values to all four equations. Then lastly, for our turning, as we can see, to turn in the positive t direction, our front left has to be positive t, our front right has to be negative t, our back left has to be positive t, and our back right has to be negative t. So we add those respective t values to our equations. And that's how we derive these four equations for our four different motors. Now taking a look at our main goal to achieve here. Our driver controller, or our perspective, the coordinate plane will always stay static. It'll never be changing or rotating. However, on the field, our robot's coordinate plane will always be rotating, changing, and shifting. So our main goal to achieve here is to actually rotate our perspective and our coordinate plane into the robot's coordinate plane. And that's what we'll be doing here today.
The way we will achieve this is by using our heading. Thanks to our Pinpoint Odometry Computer, we know our heading, also known as theta, of our robot. If you're not sure what the Pinpoint Odometry Computer is, I'd recommend you to go watch part 1 of this whole series. Using this theta, or heading, we'll be able to use a little bit of math in order to actually translate our driver perspective coordinate plane into the robot's coordinate plane, so changing from a static into a dynamic coordinate plane.
Now let's get into the math in order to make our concepts work. It's important you understand geometry to a full level. We'll be looking at the derivation of the rotational matrix in order to translate our global coordinates from the driver perspective and translate them into our robot coordinates. If you're not interested in the math or you don't understand geometry to a full level, I'd recommend you to move on to the coding section in order to understand how the coding is done. Before we dive into the coding concepts, it's first important to understand the math behind it. So first we'll go over the derivation of the rotational matrix, which will allow us to transform our driver perspective into the robot's perspective. So here I have a global coordinate plane for the driver perspective. Here I have the x plane and the y plane. So I first made a sample x and y starting position for our robot. It'll have a starting position of x, y, and it'll have a starting position of alpha theta, which we'll get from our odometry computer. From there, I've added a sample x and y called x comma y comma, which will indicate our new desired position where we want the robot to go. We've also added a new beta in order to add our existing alpha into a new heading. In this case, don't worry about the r's. The r's don't matter, but they're just a representation for the math behind the concept. Now, up here, I've created two equations for the x and y using our r and cosine and sine alphas. So x equals r cosine alpha and y equals r sine alpha. Now I've done this exact same thing for the x comma and y comma. So x comma equals r cosine alpha plus beta because we've added a beta, and we've done y comma equals r sine alpha plus beta. So now using our new equations from x comma and y comma, we can actually use trig identities in order to create new formulas. So here I have r cosine alpha plus beta will actually equal r cosine alpha times cosine beta minus r sine alpha times r sine beta. Additionally, for the bottom one, for the sine, we can do r sine alpha plus beta equals r sine alpha cosine beta plus r cosine alpha times sine beta. So if you're not sure what these identities are, you can always search them up on Google and you'll just find them right immediately. All you have to do is search up trig identities, and you'll find the ones for cosine and sine. Now let's get into the derivation part of it. So here you can see is we actually have r cosine alpha. On this board, we can see that r cosine alpha just equals x. That means we can call this section x. We can do the same thing for this section. R sine alpha, as we can see up here, equals y. Same for the bottom equation. So all I've done here now is made this math look a little bit better to the eye. I've added our rotational matrix that we just derived times our x and y old values and our x and y new values. So now what you can do with this equation is whenever you have a new heading or a new orientation of the robot, you can just plug it into these cosine, sine, sine, and cosine values. From there, you can input your x and y positions that you want to go forward to. So on the gamepad, you can push forward and take in those x and y values and plug it in, and you'll finally have your new translated x and y values for the robot to understand. So what we kind of created here is a way to translate to the computer or our robot and understand its coordinate system. Overall, this concept can now be used in our code, and now we understand it to a better understanding. Now that we've derived the rotational matrix, we'll now be incorporating it into our code using Android Studios and Java. So let's get right into that.
Here we are in Android Studios, where we'll be using Java in order to take our math concepts and make this odometry computer work and be able to do field-centric drive. So I'll be going step by step in all the codes, and in case you know something, you can always skip ahead a little bit, but I'll be going piece by piece for any beginners that are in the video. For starters, I've done the @teleop name equals field-centric teleop tutorial in order to show this code on the driver station more appropriately and in the right section. This isn't necessary, but it's a good way to organize your code. After that, I've used public class field-centric drive tutorial extends op mode. This line will be extending the op mode in order to add necessary functions into the code and make this code work. Within the public class, I've declared 4 variables. 4 of them are my motors, so back left, back right, front left, and front right. And the most important one is this odometry computer, which is called Odo. So this odometry computer has an object called goBuilda Pinpoint Driver. If you use it on your code or your SDK, you might see that it's not going to work. The reason why it's working on my side is because I've used a repository that goBuilda already created that has the file in order to build the object of goBuilda Pinpoint Driver. So in the comments, I've actually linked the repository for you to clone off of and build that code off of. That way you'll have the goBuilda Pinpoint Driver object in your files as well, and this code can work. Moving on, we go into our initiate function. In our initiate function goes our configuration. So starting off with our odometry computer, I've actually done odo equals hardwaremap.get and our class, which is goBuilda Pinpoint Driver, and then the device name on the driver station, which in my case is Odo. After that, you do the same stuff for your back left, back right, front left, and front right motors. And then you can do this, which is always optional, which is setting direction reverse. And then comes the odometry computer configuration. So for starters, you have to set the offsets, which is important because it will tell the robot where the odometry computer is, respective to the robot itself. And the values you can find is you can measure on your own, or if you're using this exact model of robot, then you can just use these values, which are already tuned for this. Next, you have to use odometry set encoder resolution. This just tells it what hardware are you using. In my case, I was using a goBuilda 4-bar pod. After that, you would use a set encoder directions, and this is just telling the robot what's positive encoder direction is. Next comes the odometry starting position. To start the odometry computer, you have to tell it where are you currently starting. That way it's not using old information. So the first step is to actually reset the position in IMU. IMU is heading, if you're not sure what that is, but that's the first step. After that, we create a starting position and we use a pose2D object because that is what our odometry is looking for. So that object will contain all our information regarding our starting position. So we'll hold our information of where we currently start and where our exact heading is respective to the field. After this, I've added some telemetry in order to debug, but again, this is always optional and you can just use it for debugging. Now comes our most important method, which is move robot. Move robot will hold all the information in order to do the field-centric drive control. So for starters, I've done this part of the code, which is double forward, double strafe, and double rotate, which all hold the values for our inputs. So these values will hold our inputs from the gamepad. For example, you can see how for the forward, I decided to use our gamepad 1's left stick Y direction. Same for the strafe, I've done the left stick X direction, and the rotate, I've done right stick X. This can always be to your preference, but me as a driver, I found these as the best possible options. Next, to actually grab the information from our odometry computer, you're going to have to use this method, odometry.getPosition. This will grab all the information from the odometry computer for you to use. Then, from that specific odometry position, I've picked apart another piece, which is just the heading, because I don't need the other information to find out the robot's position. I just need the heading. Now I do .getHeading, and I tell it in what units do I want that. In our case, we want it in radians. From there, I've actually just made it a lot easier to understand, so I've kind of just condensed the math.cosine and math.sine into their own variables. That way I don't have to keep on calling math again and again in my code. You can also see how I've done math.pi divided by 2 minus the heading, because that's the specific angle we want and respective to that robot. So this part is a really big need in our case. Now comes our implementation of the rotational matrix, which we derived in the math section of this video. So you can see how I've used forward and strafe as our old and X, Y positions. So these forward and strafe again hold the values of our global coordinate system. So by using the rotational matrix, we're actually turning the global coordinate system into the robot's coordinate system. So this is the main meat of our entire code. Then I just make it a little easier to understand, so I put all my 4 different values for my 4 different motors in an array. So for starters, I do the first one, which is global forward plus global strafe plus rotate. Then I do the front right one, which is global forward minus global strafe minus rotate. Then I do the back left, which is global forward minus global strafe plus rotate. And the last one, which is back right, global forward plus global strafe minus rotate. If you're not sure how I'm getting these positive and negative values, you can look at the section before the math session, which actually reviews over how to derive all the formulas for all the different motors. Lastly, I set the powers using our array. So since our array already has the value stored into each of its areas, I can just set the power and call those variables in. Finally, again, I just added a little bit of telemetry in order to debug in the future case. Finally, in the very last, in order to actually run this code, we use the function called loop, and that is what op mode includes. It includes this loop function that will always keep on being called in the entire code. So in that function, I called my move robot, and I've done a little bit of more telemetry calls. Again, this is very important, odometry.update. Odometry.update actually refreshes the odometry. That way it keeps updating its positions as the robot is moving. That way we're always getting the most clearest and most updated information from the robot. Lastly, I just wanted to go quickly over this loop. This loop is really good because it helps us actually also use state machine based code. State machine based code is where your robot can move in certain code bases and certain positions. That way it's not always reliant on the driver and it's more just set positions. That's why I prefer using loops for autonomous, but it's always your preference. And if you were to do linear op mode, this code wouldn't look much different. You would just call this move robot in the run op mode. Overall, this code kind of shows you how to use the rotational matrix and the odometry computer in order to actually use field-centric drive control.
I really hope you enjoyed today's video learning about how to code and get equations for the field-centric drive control. I'd really recommend you to stay tuned for part 3 where I'll go over the path planning motions and autonomous using the same hardware that you just used. Overall, thanks so much for watching and stay tuned.